Next up, we go to integration, where we are looking at the area of a bounded region. So firstly, consider the area bounded by the curve y equals to x squared, the x-axis, and the lines x equals to 2 and x equals to 5. So the area in between all these lines that we have stated here. Okay. Then that area A, as shown in the diagram, can be approximated by a number of rectangular shapes, as they have done here, right? Where if you see that these rectangles, if you find the area of the individual rectangles, you will find the area of that shape. This expands from the fact that if you have a square, and if you want to find the area of that, we can divide the square into 4 again, and find the area of each of those smaller squares, which will give us the area of the larger square. So for these rectangles, we're going to give them a height, which is going to be at the curve, and their width or their thickness is going to be just delta x. Now we did this slightly in differentiation, where delta x just means a very small increase in x, so a very small x value. The approximation for this area is then obviously the area of the rectangles added together. So the area of the rectangle, which is just y multiplied by, so y is the height, multiplied by the thickness, which we have named as this, delta x. And if you take the sum of all these rectangles, which you can write like this is the summation symbol. So if you take the sum of all those rectangles, you're going to get the approximation of this area A right here, based on these rectangles. Now, the thinner we make the rectangles, the better our approximation is. So for example, if we had this same thing, but we divide it into just 2 rectangles, we're going to take either this y value, which is going to give us this rectangle right here, and we're going to take this y value, which is going to give us this rectangle right here. And if we add up the areas of these 2 rectangles, we're not going to get a very good approximation, because we're going to have all of this area that's extra. So the thinner the rectangles are, the smaller the thickness, the closer the approximation is. Remember, the thickness is shown by this thing right here. As the thickness approaches 0, meaning it becomes extremely thin, obviously you are getting very, very close to what the area actually is. We actually show that as the integration of y, which is your height, multiplied by dx. Dx is the smallest possible value you can have for x, right? We saw dx in the dy over dx, so this dx is like a very small difference in x. And we take the integration of it from the limits 2 up to 5. Therefore, this right here will be the actual representation of what the area is. It's not going to be an approximate answer, it's going to be the actual answer. So if y is equal to f of x is a function with y greater or equal to 0, then the area A bounded by the curve y equals to f of x, so the function, the x-axis, and the lower limits and the upper limits. Here we have 2 and 5, we're giving a general value a and b, is given by the formula. So the area is given by the formula. The area is given by the integration of y with respect to x, with the lower limits of a and the upper limits of b. Remember, y is just a function of x, right? So for example, in this case, it would just be the integral from 2 to 5 of x squared dx. Okay, so let's take a look at this example. We want to find the area that's bounded by the function, so y equals to 3x squared, the x-axis, and these 2 lines here, x equals to 4 and x equals to 6. And we just showed how to find this area right here. The way we're going to do it is, we take the integral of the height, which is y, multiplied by the smallest x, dx, with the lower limit of 4, the smaller x, and the upper limit of 6, the bigger x. And we're just going to integrate this, and that is going to be our area. So expanding this, we have area is equal to the integral from 4 to 6 of 3x squared with respect to x. Integrating this right here will give us 3 times x cubed over 3. Remember, power n plus 1 divided by n plus 1. And that is just going to be x cubed. That's the integral of this right here. Then we're going to apply our limits. We did integration. Apply our limits 6 and 4. This is just going to be 6 cubed minus 4 cubed. And that is going to be 216 minus 64, which is equal to 152. Therefore, 152 units squared, obviously we don't have whether it's centimeters or meters or whatever, so we just give it units squared because it's the area. Example 2, find the area of the shaded region where it is bounded by the curve y equals to x squared minus 6x, the x-axis, the line at 0, x equals to 0, and the line at x is equal to 6. And the way we're going to write that is, our area is equal to the integral from 0 up to 6 of y with respect to x, which is equal to the integral from 0 to 6 of x squared minus 6x with respect to x. Integrating this right here will give us x power 3 over 3 minus 6x squared over 2, which is just equal to x cubed over 3 minus 3x squared. And then we apply our limits of 6 and 0. Applying 6 here will give us 6 cubed, which is 216 over 3 minus 3 times 6 squared. And then we're going to subtract it by 0 cubed over 3, which is 0, minus 3 times 0 squared, which is also 0. And so we're going to have this right here as our area. And that is going to be 72 minus 108, which is equal to negative 36. Now, if you notice, we got a negative answer, and that is because our area was under the. Therefore, the area of the shaded region is going to be 36 units squared. Remember, you don't write the negative because the negative just implies that that area that we found was under the x-axis. So that's going to be our answer. Now, suppose we were given this curve right here, okay, where y equals to x cubed minus 4x is the function, and our limits, our leftmost limit is negative 2, and our rightmost limit is positive 2. And I've already done this integral just to show you what happens if we go from negative 2 up to 2. So integrating x cubed minus 4x, we get 1 over 4x power 4 minus 2x squared. We apply our limits of 2 and negative 2. And what that will do, it will give us the same answer on both ends. And therefore, if we subtract the 2, we're going to get 0 units squared. Now, this shaded area definitely is not 0, right? But the reason we got 0 actually expands from the example that we just did, where if we get an area below the x-axis, we're going to get it as a negative. And if we get the area above the x-axis, we're going to get it as a positive. But we want the area generally, right? So what we will have to do in this case is take the area of each region individually. So name this as A, name this as B, find the area A, find the area B, then you'll just add the 2. Or you can say add the absolute value. So for that, we'll need to know the upper and lower limits of both of these regions. So the lower limit of A is negative 2, upper limit of A is 0, lower limit of B is 0, and upper limit of B is 2. This gives us this evaluation right here. Obviously, the integration part stays the same. Our two limits are going to be 0 and negative 2, which gives us 4 units squared. And the other side is going to be 0 and 2, which is going to give us again 4 units squared. Obviously from negative 4 since it's below the x-axis. And so the total area, we'll just add the 2, both in positive form. That will give us 8 units squared, which is going to be the actual area under the curve from negative 2 up to 2. So we have to be very careful when evaluating areas because of this negative side that we have. Let's do an example of just that. We're told to find the total area of the shaded regions. We have this above the graph and this below the graph. Now, if we just take the limit from 0 up to 6, what will happen is, obviously this is a negative, and this seems like the area is larger here. And this is a positive and the area is smaller. So the answer we will get will be a negative answer if we just go from 0 up to 6. But it won't be entirely correct because what we would have done is taken this negative area and basically removed this part of it from here. And that's what we would get if we did 0 up to 6. But instead we have to treat them differently. So 0 up to 2 the first time, then 2 up to 6 the second time, then we're just going to add the 2. So we want to find the integral from 0 up to 2 of x times x minus 2 times x minus 6. We're going to add it with the integral from 2 up to 6 of x times x minus 2 times x minus 6. This x times x minus 2 times x minus 6 is just x cubed minus 8x squared plus 12x. And so we want to integrate this right here with respect to x. Integrating this would give us x power 4 over 4 minus 8x cubed over 3 plus 12x squared over 2. And again, simplifying this will give us x power 4 over 4 minus 8x cubed over 3 plus 6x squared. We're going to apply the limits of 0 and 2, and then we're also going to apply the limits of 2 and 6. Applying limits of 0 and 2 will give us 2 power 4 over 4 minus 8, 2 power 3 over 3 plus 6, 2 power 2. Subtracted by applying 0 into this, which will just be 0 for this, 0 for this, and 0 for this. So we're going to just minus by 0. And then what we want to do to this is add it with the other side of the limits as well. So 6 and 2. And when we put in 6 into this, we will get 6 power 4 over 4 minus 8, 6 power 3 over 3 plus 6, 6 power 2. And obviously we have to subtract it by the 2 side of it. So minus 2 power 4 over 4 minus 8, 2 power 3 over 3 plus 6, 2 power 2. This will give us 6, 2 over 3 as our area of the blue side, the one above the x-axis, and that we have to add it with the area of the red side below the x-axis. And the area of the red side, obviously the one when you put 6 in, will be negative 36. And when you put 2 in, we're going to have the same 6, 2 over 3. So we're going to subtract 6, 2 over 3 from that. And this right here would be negative 42, 2 over 3. Now obviously when you're adding these two, if we would have done straight away from 0 up to 6, the sign would have been added as it was. So it would be 6, 2 over 3 minus 42, 2 over 3. That's why we would have gotten a smaller number. But because we're doing it differently, we have to first change this into a positive because we're finding the area. And therefore this right here would then become positive 42, 2 over 3. And adding it with the initial 6, 2 over 3 of the blue side, we're going to get the total area of 49, 1 over 3. That's going to be the total area of the shaded regions right here. Now, until now, we have looked at the area bounded by a curve and the x-axis. But we can also integrate the area bounded by a curve and the y-axis. So instead of integrating with respect to x, which has dx as our integration term, we will integrate with respect to y. So we'll have dy as our integration term. So if x is equal to f of y is a function with x is greater or equal to 0, then the area bounded by the curve, x is equal to f of y, the y-axis and the lines y equals to a and y equals to b is given by the formula a equal to the integral of x with respect to y from the limits a to b when x is greater or equal to 0. So everything remains the same, just that now instead of using x values, you're using y values. Let's look at this as an example. So there is an equation x is equal to y times 4 minus y, which is just 4y minus y squared. And we want to take the area from the lower limit of 0 up to the upper limit of 4. And the way we're going to do this is just integrate from 0 up to 4, 4y minus y squared dy, right? Because this right here is what x is. These are values of y, remember? And so we're just going to integrate this with respect to y. We're going to get 2y squared minus y cubed over 3. And this we have to put in the limits of 0 and 4. We will get 2 times 4 squared minus 4 cubed over 3. And all that subtracted by the 0 part, which will just be 0 because 2 times 0 squared is 0 minus 0 cubed over 3 is also 0. And this right here, 4 squared is 16 times 2 is 32 minus 4 cubed is 64 over 3, which is 64 over 3. That gives us 10, 2 over 3 units squared. So that right there is going to be the area that is bounded by the curve, the y-axis, and these two limits, 0 and 4. Next, we have a similar question, but now instead we have been given an equation in terms of y. So again, let us go back to the formula. It was the integral from the lower limit a to the upper limit b of x with respect to y. Okay. But here we do not have x, we have y instead. So what do we have to do here is make x the subject. So if y equals to square root of 3x plus 1, then y squared is equal to 3x plus 1. Subtract 1 on both sides, we have y squared minus 1 equals to 3x. We can divide by 3 on both sides, we have y squared over 3 minus 1 over 3 is equal to x. I've already separated it so that the integration is easier. Therefore, this is now the equation in terms of x, and we can now just integrate it to find the area. So integration of y squared over 3 minus 1 over 3 dy from the limits of 1 up to 4. Yes, and so we're going to integrate both of these. Y squared over 3, we're going to integrate it, we're going to get y cubed over 9, subtracted by the integration of 1 over 3, which is just going to be 1 over 3y. And we're going to put in the limits of 1 and 4. Putting 4 in, we get 4 cubed over 9 minus 1 over 3 times 4. And then subtracted by putting 1 in, we have 1 cubed over 9 minus 1 over 3 times 1. Remember, you're subtracting by the entire right side when you put in 1. Then this entire thing will just evaluate into 6 units squared. And that right there is going to be your answer for the area that's bounded by this shaded region right there. So we have looked at the area bounded by a curve and an axis, the x-axis and the y-axis. But what if we have a curve and a straight line? So suppose we are told to find this shaded region right here. What we can do is calculate the area of each with any of the axes and subtract from one another. The way this works is, obviously if you want the area in blue, we can find the area bounded by the curve and the x-axis, which is going to be this thing right here. Yes? Then we can find the area that is bounded by the line and the x-axis, which is going to be this thing right here. Obviously with the other bounds being the x equals to 1 and x equals to 6. And what can happen here is if you take the blue area, which is the entire curve up to the x-axis, subtracted by the red area, which is from the line to the x-axis, then we would get the remaining, which is the blue shaded area. And that's how we're going to do it. So find area under the graph y equals to negative x squared plus 8x minus 5, and you're going to do that by integrating the limits of 1 and 6. Remember, limits are x values, so 1 and 6 of negative x squared plus 8x minus 5 with respect to x. This right here is going to give us negative x cubed over 3 plus 4x squared minus 5x, and you want to put in 1 and 6 as your limits. This will evaluate to give us 43 1 over 3 units squared. And this area bounded by the straight line, you can see it's a trapezium, okay? This trapezium right here. So it looks something like this, where this is of length 2, this is of length 7, and this is of length 5. The way you find the area of a trapezium is just half times side 1 plus side 2, so 2 plus 7 times height, which is 5. And that will give us half times 9 times 5, which will just be 22.5. And then that is the red area. This is the blue area that I colored in. And if you subtract the two, minus 22.5, we will get 25 over 6 units squared, which will be the area that was shaded initially that we have to find. We could also integrate this equation, by the way, in order to find the area under the line. But I just found that because we know the area of a trapezium, that would be easier to calculate. There is another method, however, to find the shaded area. And so imagine there is a function f of x, which is by the blue line. There's a function g of x, which is by the red line. The area between the two curves will be calculated by this thing right here. So we remember doing this law. We said that this thing right here, the integral of fx minus g of x with respect to x, is the same as the integral of f of x with respect to x minus the integral of g of x with respect to x. That's what we're going to do here. We have two options. One is we can subtract the two functions initially, then integrate it, or we can integrate it differently and then find the answer from that. So let's look at this method right here. So what we will do is we will subtract the two functions first, then integrate it. So we have negative x squared plus 8x minus 5 subtracted by x plus 1. And this will give us negative x squared plus 7x minus 6. And we're going to integrate that with respect to x from 1 up to 6. And integrating this will give us negative x cubed over 3 plus 7x squared over 2 minus 6x, and we're going to put in 6 and 1. And this right here will give us 25 over 6 units squared, which is the same answer that we got with the other method as well. This is a final example. This is an example, and we're going to do something a bit different for this. I'm going to explain a bit more. So we want to find the area between the two curves right here, one curve and one line. But we see that there is a part of it which is below the x-axis, there's part of it which is above the x-axis. And this might tell you that there will be a problem if we take the limits from 1 up to 7. So you initially might think that we need to find this value, then integrate side by side. But that's actually not necessary. Why? So suppose we were to find the area under the graph for 2x minus 9. Okay? So we integrate 2x minus 9 with respect to x from 1 up to 7. What would happen is this part would be taken as negative and this part would be taken as positive, this entire triangle right here. Okay? Therefore, this is going to be removed. Okay? This part right here is going to be removed from the area, while this part is going to be added by the area. Now, this removal is correct. We actually need it to be removed fully. Okay? This addition has an extra bit that has to be removed that comes from the curve actually, right? So let us now look at the curve part of it. So suppose we were integrating the curve x squared minus 6x minus 2 with respect to x from 1 up to 7. And I'm going to erase the shaded part so that we have something else that we're dealing with. What this integral will give us will be negative from 1 up to the point where it intersects the x-axis. So this part is going to give us negative, while this part right here, this tiny part above the x-axis, will be positive. And if we integrate it fully, obviously these positives and negatives will do their thing, and at the end will give me a final answer after they've already removed from each other. They've already cancelled each other out, part of it obviously. However, what we see here is we actually want the opposite thing to happen. So we want the red part to actually count, and we want this part to actually not count. So what we just can do here is switch the sign of it. So with both of these combined, what we will have is this red section that is counted, there is a plus, so it's counted. We want to have it in our final answer for this curve right here, with the negative part that we had from the other line integration, from this one right here. We counted this as a negative. Therefore, whatever is below the x-axis will be accurate. When we look at above, we had that entire triangle to be counted. Okay? And now we have that this part of the curve is going to get taken out. Therefore, what we'll remain with is this exact blue shaded region that they told us to find. So we can just integrate this like this and find the final answer. What we will get from this one is x squared minus 9x, and we put in 7 and 1. Then we want to subtract it by x cubed over 3 minus 3x squared minus 2x from, again, 1 to 7. And we're going to put a bracket here just so that we are subtracting by this entire thing. Doing this will give us 49 minus 63 subtracted by 1 minus 9. Then you're going to subtract by the entire right side, which is going to be 343 over 3 minus 147 minus 14 subtracted by putting in 1 into these. 1 over 3 minus 3 minus 2. And that will give us our final answer, this entire evaluation, which will be 36 units squared. And that is going to be the blue shaded area that we had to find.